Welcome to our fluid dynamics simulation demo. You might be wondering why we have targeted a GPU instead of a CPU. In 2003, GPUs and CPUs were able to do a similar number of calculations per second. Since then, the GPUs have steadily increased in performance over CPUs in the sheer number of calculations that they're able to compute. In 2006, GPUs were already pushing 350 gigaflops, as opposed to CPUs, which were only processing around 50. This only warranted a further investigation as to how to utilize such a resource for scientific computing. We explored CUDA, a general-purpose GPU programming utility from NVIDIA. CUDA is developed in a special version of C that contains a few extensions to allow the programmer to specify where functions and memory are allocated, being on the device or the host machine. It integrates well into Visual Studio, which allows to develop in a familiar environment. However, the greatest advantage is that CUDA works on any 8000 series or above processor. Our goal was to simulate fluid flow, and to do this we used the Lattice-Boltzmann method. We chose this method because it had a high degree of parallelization inherent in the algorithm, and it is an accurate approximation of the Navier-Stokes equations, the de facto equations used for fluid motion. In the method, space is broken down into lattice. The calculations to figure out the state of a lattice are done solely by looking at the previous state's configuration. This allows us to update each lattice in parallel. An example of a practical application would be to determine how fluid flow would behave with obstacles in a system. We will now demonstrate our simulation running on the GPU. In this simulation, we can think of the system as a fluid flowing through a pipe, where the fluid is coming from the left side and flowing towards the right. At the top and bottom are the walls of the pipe. The colors in this system represent the different velocities of the fluid at each point in the pipe, from very low velocity, represented by a dark blue, up to high velocity, represented by dark red. Using our mouse, we can dynamically add obstacles to the simulation. Let's add a C-shaped obstacle into the middle of the pipe. The fluid flows from the left to the right, but avoids the obstacle we have created in the simulation. Notice the flow is now traveling around the obstacle we have just placed, as opposed to flowing through it. The fluid velocity in front and at the back of the obstacle is low, as indicated by the dark blue colors, while the velocities on the sides of the obstacle are high. On the NVIDIA 8600 GTS card, the simulation is currently running above 60 frames per second. Compared to a MATLAB equivalent fluid simulation running on the same system, which visually appears to be running at 2 to 3 frames per second at a lower resolution, our simulation on a GPU is good enough to be considered real time. Another great feature of CUDA is its ability to scale. We specifically targeted a commercial-grade graphics card. However, NVIDIA offers another series of GPUs. Tesla is specifically designed for processing massively parallel applications. You can easily make systems that invoke 128 GPUs and attach it to your desktop to unlock a massive amount of processing power. Using a system like this with our simulation would allow you to easily compute systems in a far higher resolution than what we have shown here today. Thank you for watching our demonstration. I hope you are as excited about physical simulations calculated on GPUs as we are.